Hello everyone. Can you all hear me? All right. So today I'll go over just a little bit of midterm 1 practice. I have the WebWorks and I have the textbook in front of me. So feel free to ask any questions in the comments. Let's start with the area between curves. Okay, so suppose we have this example. And you want to find the area enclosed. Then the first thing you have to know is how they intersect. So if you know the sketch, then it's not too bad. So at 1, it's 0 for this curve. So this curve will be y equals root x minus 1. And then x minus y equals 1 is the same as y equals x minus 1. So it's just a straight line. Crosses, so it's at -1, and then when x is 1, it's at 1. So it'll intersect here, and then we'll just keep going. So we have another point of intersection. So we want to figure out where that point is. Okay, so let's do that. So for this one, it's not too bad. All you have to do is just set them equal to each other. So this is going to be x minus 1 equals square root x minus 1. And then just square both sides. So x minus 1 square equals x minus 1. And then if we assume that x is not equal to 1, and we don't really need the x equals 1 because we already have our intersection x equals 1 here. Then we can just divide both sides by x minus 1. So we'll get x minus 1 equals 1. So x equals to 2. So this point has to be 2. Now, if you could just kind of see it, because these numbers are so nice, that if you do 2 minus 1, that's 1, and then 2 minus 1 is 1, then you don't need to go through all this. Just figure out that it's 1 and 2. But now that we have that, we just integrate the top curve minus the bottom curve. So from 1 to 2 of the top curve is root x minus 1 minus the bottom curve is x minus 1 dx. Oops. Okay. So there's many ways to integrate this, but let's just do one way where it's u substitution. So let's let u equal to x minus 1, then du is dx. And so when you do that, you get this is a square root of u minus u, and then du. And now let's review how to change the bounds when you do substitution, but that's pretty easy. This is x equals to 1, so just plug this into here, and you get u equals to 1 minus 1 is 0. And when you plug in x equals to 2 into here, you get 2 minus 1 is 1. well, u equals 1. And then you just integrate. So the antiderivative of u to the 1/2 is u to the 3 over 2, 2 over 3, minus 1/2 u squared. And then you plug in 1 and 0. So that's just 2/3 minus 1/2, which is 4 over 6 minus 3 over 6, so 1/6. And so that's how you do that. So that was not too bad. But now let's do it using dy integration, but for the same problem, just for practice. So okay, so these are our two functions. For this one, we need to figure out where the y bounds are. So y equals 0, and then it goes all the way up to this point. This point is if you plug in 2, you know that y equals 1, so it goes from 0 to 1. And then for the y bounds, you do the right curve minus the left curve. But when you do that, you have to use what x equals to. So this curve, x equals y plus 1. And then this bottom curve, x equals, you solve for it, so you do square and add 1. So x equals y squared plus 1. Okay? And then this integral will be from 0 to 1 of the right curve is y plus 1 minus the left curve is y squared plus 1 dy. And so this is just 0 to 1 of y minus y squared dy, which is a much easier integral. So this is 1/2 y squared minus 1/3 y cubed from 0 to 1. And so it's 1/2 minus 1/3, which is 1/6. Okay, so sometimes doing a dy is a lot easier. All right, so that was area between curves, and now let's review the volumes. So how about y equals x cubed, y equals 1, x equals 2. And then, so this is the region. And then you rotate about y equals -3. All right, so let's first sketch the graph. So y equals x cubed looks like this and like that. Y equals 1 is here. X equals 2 is going to be out here. So it's going to be this region. And if you want to figure out where this y value is, all you do is plug in x. So 2 cubed is 8. And then over here would be the cube root of 1, which is 1. And you want to rotate it about the line y equals -3. So it's going to spin around like that. But for these volume ones, you don't really need to know how the shape looks like. You just know that the line that you're rotating about, this is where your center is going to be. And then you have an inner and an outer radius. So sometimes that inner radius is 0, but in this case, your inner radius is from here to here. So inner radius. And your outer radius is going to be from the center all the way out. So just by inspection, it looks like your inner radius is going to be constant and your outer radius is going to depend on x. So your inner radius is, it's going to be 3. It's not drawn to scale, but it's this 3 units and then 1 more. So it's in total 4. And your outer radius is, it's going to be, so y equals x cubed, or x cubed gives you this much. But you only want, well, not you only want, you want all of the green part. So you have to add 3 units. So your outer radius is x cubed plus 3. And then once you have that, the rest is pretty straightforward. The volume is given by pi, can't forget that, times the integral. We're going dx because we're cutting it up this way and we're going that way. So 1 to 2 of the outer radius square. So x cubed plus 3 squared minus 4 squared and dx. So to do this integral, you just multiply it out. This will be pi and 1 to 2 of x to the 6 plus 6x cubed plus 9 minus 16 dx. And so if you take the antiderivative, it's going to be 1 over 7 x to the 7 plus x to the 4, 6 over 4 plus, I guess minus 7 x, and then all over 2, or not all over. You evaluate from 2 to 1. So I won't really do that, but that's the answer. So any questions with this? Okay, so those were the ones that were on the midterm practice. Let's do one more of these volume ones. Oh, and if you're reading the book, don't worry about doing volumes using cylindrical shells. We're going to skip that. I mean, it's not that bad, but yeah, we're not going to get too worried about that. Okay. So how about x, y equals 1, y equals 0, x equals 1, x equals 2. That's the region. And we're rotating about the line x equals -1. So let's... Sorry, oh crap. Would we be able to leave that? Yeah, you can just leave that on the exam. I mean, it'd be nice if you find the number. No, the midterm only covers up to volumes. Anyways, so this is a type that I think we haven't really done before, or at least I haven't. So first we need to sketch the graph. The graph of xy equals 1 is you can solve for x or y. So let's solve for y. So it's going to be like 1 over x. So it's here and here. And then your other bounds are x equals 1 and 2. Yeah, sorry. And then y equals 0. So y equals 0 is the x-axis. So it looks like it's this region. And now you're rotating it about the line x equals 1. So let's get rid of these. And we're spinning it around this way. Not that the shape really matters. Because again, all you need is you know where your center line is, and then you need to compute the inner and the outer radius. Although with this one, it's a little funky because the inner and the outer radius change. Namely, at this point. So we split it up into 2 regions. So this point is x equals 2, which means y is 1 over 2, because this is the graph 1 over x. So this is at 1/2 and 0. And then at 1, x equals 1, y is equal to 1 over 1. So that's 1. Now, you might be thinking, isn't it easier if we just do dx then, because the top curve and the bottom curve don't change? But for this is a volume one, so it's not like top or bottom. Right? We have to rotate it this way. And I guess this example would have been kind of easier if we had covered the cylindrical shells method, but then again, that's just another new method to cover. So let's not do that if we could just solve this problem like this. Okay, so let me call this portion volume 1 and this portion volume 2. Volume 2 is clearly very easy because it's just a cylinder. Well, a cylinder with a hole in it. So anyways, volume 1. How to compute that is we need to find the inner radius, which is from this point all the way out to here. Inner. And the outer radius is going to be from the center. Maybe I'll use this. All the way out to here. So how do you compute the inner radius? So this much is x. which if we solve for x, oh no, we don't need, sorry. This part is just constant, this is 1. And then, but we want the whole green line, so it's going to be 1 plus 1. So the inner radius is 2. The outer radius is, so from here, the y-axis all the way out to here, this is given by x, which equals 1 over y. So it's 1 over y plus this much. So it's going to be 1 over y plus 1. But then once you've identified the inner and the outer radius, then the rest is pretty standard. So this is the hardest part. So let me just go over it one more time. So the inner radius is from this point all the way out to here. We know that from here to here is 1, and it's going to be the same. So that's just 1 here, but then you have to start from the center. So you add another 1. So it's 1 plus 1, so that's 2. Your outer radius is you start from the center line and go all the way out. So you want this much. And this much is given by 1 over y. You want to have it in terms of y. And then you add an extra factor of 1. So you have that. And so we want to find the volume of the top part. And so that's going to be pi times the integral, outer radius squared minus inner radius squared. And it's going to be dy. So what should the bounds be? It's going to be from this point, which is 1/2, all the way out to this point, which is 1. So your integral is going to be from 1/2 to 1. And with these volume problems, a lot of them, you just kind of multiply it out and integrate. Like this one is the same. This is pi times integral 1/2 and 1 of, if you square this, you're going to get y to the -2 plus 2 times y to the -1 plus 1 minus 4 dy. And so you just integrate. Well, actually, let's do this. So this is pi times y to the -1. You add 1, and then you divide by 1. So that's the same as, sorry, you divide by -1, which is the same as putting a negative sign. And then this one is, you don't add 1 because you can't. This is natural log of y minus 3y, because, well, minus 4 is 3, or minus 3. And then you plug in 1/2 and 1. So that's going to be some number, but we're not done. We still have to compute this part, volume 2. Volume 2, you don't really even need calculus. You just know what the shape it looks like. It looks like this. The inner radius here is this length, which is 2. And the outer radius is all the way out to 2. But then you have 1 more, so it's 3. And so you do pi r square of the outer minus inner. So it's pi times 3 squared minus 2 squared multiplied by the height. The height is just 1/2. And so you can compute that. If you use integrals, you get the exact same thing. So any questions of this? All right, any questions from WebWorks? Enclosed by 3 curves. Okay, let's do an example. I mean, this is probably not what you're talking about, but you can have like a curve and another curve, and then straight lines are curves. So yeah, that's enclosed by 4 curves. So let me see if I can find an example in the book where it's enclosed by 3 different curves. Not really. But okay, how about an example where like the top and bottom functions switch? So yeah, this one. The area, this area now, of y equals sine of x, y equals cosine of x, and x equals 0 and x equals pi over 2. Okay, well, so first let's sketch these 2 functions. But only up to pi over 2. So let's see. Sine starts, goes to 1, or starts at 0 and goes out to 1 at pi over 2. And then cosine starts at 1 and lands at 0. And so what you'd have to do is find the intersection point. So you have to know when sine equals cosine. Which happens when it's an equilateral no, that's an isosceles triangle, right? Because on the unit circle, sine and cosine are like the what's it called? This, this and this, adjacent and opposite. And when that's the same, so it's 45 degrees, so pi over 4. So this happens at pi over 4, or when tangent is equal to 1, which is also pi over 4. So we know this is pi over 4. And then to find this area, you just integrate from 0 to pi over 4 of the top curve, which is cosine, minus the bottom curve, plus pi over 4 to pi over 2. And then the top curve changes, so sine x minus cosine x dx. So if you integrate this, then you'll get your answer. Okay. So web work assignment 2, first integral in question 5. Ah, gotcha. So the numbers are probably going to be different, but what I have is negative 14 to 1 of s and the absolute value s squared ds. So this is actually similar to what I just did. You want to split it up into parts where you know what the sign of the absolute value is, because absolute value is x when x is positive, and negative x when x is negative. You put a negative sign because x is negative, so negative negative makes it a positive. So first of all, where is 49 minus s squared equal to 0? It's going to be at 7 and negative 7 is when 49 squared equals 0. When 49 minus s squared equals 0. So now you have to figure out when it's less than negative 7, then is the inside expression positive or negative? So when it's less than negative 7, like negative 8, then that's like 64, which is bigger than 49. So this side is negative. When it's greater than negative 7 but less than 7, then the inside expression is positive. You can plug in like 0 or something. So it's positive. Now, you're only integrating from negative 14 to 1. So you don't really need the remaining parts. And how we're going to split this is it's the integral from negative 14 to negative 7 of s 49 minus s squared ds plus the integral from negative 7 to 1, so just this much, of s times 49 minus s squared ds. But you know that in this interval, negative 14 to negative 7, this inside expression is negative, so you would just put a minus sign to make it positive. So this is negative 14 to negative 7 of s times s squared minus 49 plus negative 7 to 1 of when it's between negative 7 and 1, then the absolute value does nothing. So this is s times 49 minus s squared ds. Okay. And then you just multiply this in and you integrate as usual. And you can't really combine any of them because the signs aren't correct and the bounds of integration are different. So you have to do this. But anyways, I'll let you do that. WebWorks 6. Oh, okay. The integral from e to the 9 dx and x and root natural log x. So for this, basically with all these substitutions, you want to make them. Like, this is not really a rule, but you want to use. You want to pick your substitution as the most complicated part. It's not always like this, but in this case, it's going to work. So you let u equal natural log of x, and then you just kind of hope that something nice happens. So if you let u equal to natural log of x, then du is 1 over x dx. And then something nice happened because you have a 1 over x dx. So you can rewrite this as du over square root of u, because dx over x is du, and then this is root u. And then if you plug in e into here, natural log of e is 1. natural log of e to the 9 is 9, because natural log of e to the 9 you can think of as 9 comes down. Natural log of e is 1. So it's just 9. Okay. And then this is just u to the negative half from 1 to 9 du. And so the antiderivative is u to the 1/2, because you add 1 and then you divide by this, which is the same as multiplying by 2. Or another quick way to do this is just quickly take the derivative. So 1/2 and 2 cancel out, and there's nothing here. 9 and 1. So this is 2 times. Square root of 9 is 3. Square root of 1 is 1. And so you get 4. So any questions with this? All right, any other questions? All right, well, if not, then let me do one more interesting substitution one. Like this one. So antiderivative of this. And here's one antiderivative you're going to have to know is the antiderivative of 1 over 1 plus x squared is arctangent of x plus c. Because the derivative of arctangent is 1 over 1 plus x squared. So this one is tricky because you look at it and you try doing your substitution, but it doesn't really work because, so let's say you do 1 plus x squared, then du is 2x dx. So 1/2 du is x dx, and you think, oh, there is an x dx, except you can't because there's a 1 plus there, right? So it doesn't completely cancel out. Or in like a really weird notation, this is kind of like dx plus x dx, 1 plus x squared. So you can only get rid of this, right? You can't get rid of that term. So this isn't going to work. But what you can do is split up the integral into 1 over 1 plus x squared dx plus x dx, 1 plus x squared. And in this one, you have just an x dx, so you can integrate it. This one is just one of the basic ones you have to know. So that's how you would approach this problem. So I guess if I was to do it real quick, u equals 1 plus x squared. So du is 2x dx. 1/2 du is x dx. So over here, this is arctan. Plus this is going to be integral 1/2 du over u. So arctan of x plus 1/2 natural log of u. But u is 1 plus x squared. And then plus c. So sometimes you have to split up the integral. Anyways, can you go over how you solve the fourth substitution problem? Oh, yeah, that one. Zero to 4 x 1 plus 4 x dx. Maybe I won't use red. It looks kind of crappy on the screen. Anyways, so a lot of times if you just pick u as the most complicated part, and then something good happens. So if you let u equal to 1 plus 4x, then du is equal to 4 dx. So 1 4 du is dx. Okay, so this integral becomes square root of u, and then dx is 1/4 du. But what about x? Well, you can just solve for x here, right? So this is the same thing as u minus 1 over 4 equals x. And so just substitute this x into here, and you get an expression that is just in terms of u. And so this will be 1 over 16 u minus 1 over root u du. And then we just do the same trick as the previous thing. So you just split it up. Du minus 1 over root u du. So you get 1 over 16 of root u minus u to the 1/2, negative 1/2 du. And then, well, I forgot to change the bound, so let's do that right now. When x is 0, you plug that in, u is equal to 1. So this would be 1. When x is 4, you plug this in, and you get 16 plus 1 is 17. So just find the antiderivative and plug it in, and you'll get the answer. Okay? So let's see if there's any other fun ones. They're all kind of easy. They're not easy. How about this? Practice midterm area between curves question 2. Okay. So the curve is 1/4 x squared. And this is 2x squared. And x plus y equals 3. And x is greater than 0. Okay, so x plus y equals 3 means this at 3 and 3. And then y equals 2x squared would look like this. And then y equals 1/4 x squared would be less than this. So this would be like this. So 1/4 x squared. Wait, is it? Yeah. This is y equals 2x squared. And then this is going to be x plus y equals 3. And then it's x positive. So it's this region. Okay, so this one, It doesn't look like there's an easy direction. They're gonna both require that you do two separate integrals. So let's just do that. Unless, let's see. No, not really. I was thinking maybe if I just do this and find that area and then subtract from that. But then that's still doing two integrals. So, and you would still need to figure out what the intersections are. So it's not really saving any work. Okay, so let's just do that. So first find the intersections. We'll do it using dx. So the intersection between x plus y equals 3 and y equals 2x squared is x minus 3 equals to, no. 3 minus x is equal to 2x squared. And so this is the same as 2x squared plus x minus 3 equals 0. So this is going to split up as probably plus 3 and minus 1, because then you get minus 2 plus 3 is x, and then, yeah, so this works. So you get x equals to negative 2 over 3, and x equals 1, which happens, so this must be at 1. So then where is the negative 2/3? Where is that? Well, remember that the 2x squared graph goes like this, and then this is a line, so it'll keep going like this. So somewhere way out here, actually it's not way out here, it's just negative 2/3. It'll intersect again, but we're not really concerned with that because x has to be non-negative. So that's our first value for x. And then our second intersection is this. So that's when 3 minus x is equal to 1/4 x squared. So multiply everything by 4. So you have 12 minus 4x equals x squared. So this is the same as x squared plus 4x minus 12. So this splits as 6 and 2. Yeah, x plus 6 and x minus 2. And then same reason, somewhere out there. Actually, at x equals negative 6, it's going to intersect, but we aren't really concerned with that. This point here is 2. And so we split the integral from 0 to 1 and 1 to 2. The top function here is 2x squared. The bottom function is 1/4 x squared. And then the top function here is y equals 3 minus x. And the bottom function is 1/4 x squared. Okay? All right. Is it not negative 3 over 2? Yeah, that's right. But yeah. But anyways, it doesn't really matter because it's non-negative. So any other questions? Yeah, I mean, hopefully you guys can get it from here. Okay, maybe I'll do one more integration. Trying to find a hard one. But all the integrals, at least up to midterm 1, are not that bad. Midterm 2 integral and final integrals are going to be pretty bad. Oh, earlier you mentioned that we aren't doing the area of what again? Oh, I guess I just wasn't creative enough to see like a region bounded by 3 curves. And I guess this is an example of 3 curves. I don't know. Yeah, there's really only 2 types of areas. It's either top and bottom or left and right. Sometimes you have to like switch which one's the top one, which one's the bottom one. And then I guess it could look like that. So you have to split the integral from here. It'll be this is the top one, this is the bottom one. From here to here, this will be the top, this is the bottom. But then a lot of times with these types of ones, you can do right minus left and do one integral. But the area problem that we just did seems to be a problem where you can't, or not you can't, there's just no way out of doing 2 separate integrals. In general, for midterms, well, just area between curves is this, 5-ish, like 5 with multiple parts. Volume using cylindrical curves. Yeah, you don't have to worry about that. It is an interesting topic, though. So it's, I guess the point is, suppose you want to integrate a curve that looks like this, then there is no like insider, I guess. What I want to say is this is just given by one function. And so how do you compute the inner and the outer radius of these things? Well, it could get kind of complicated. But then if you use cylindrical shells, then you're basically taking these rectangles and you're rotating them. So the formula is slightly different. But you don't have to worry about that, at least for midterm 1. Like all the volumes are going to be nice and they're given as functions. Okay, let me end with this integral. So these are the ways where I can sort of mess with you guys if I wanted to. I probably won't, but who knows? So given this type of integral, like that, maybe even here. No. No, even this is actually too easy. I guess the trick that I wanted to like use was completing the square, but then you don't really need to actually with this one. This one you just use this. Just that u as the most complicated part, and du is equal to 2x plus 2 dx, which is just 2 times x plus 1 dx. So that's kind of a boring problem. But if I wanted to cook up something complicated, well, since I'm struggling to come up with something complicated, you probably won't see anything complicated from the midterm. Yeah, if you only know substitution, there's just not very many integrals that I can ask. It's only until we get to chapter 7 that we can see like the really, really crazy integrals. Well, anyways, any more questions? Okay, well, it's almost an hour, so I guess I will end it here. I'll see you guys on Monday.